like that's why they don't use.
That's why they don't use cows.
All right, we're gonna be back on track, Isaac. I hope this is relevant.
Total speed or just speed in the direction of the field?
Total.
Okay.
What about the units?
Not needed.
Oh heck yeah! This is mostly because I don't have to think that hard. This is why I like it. I like physics when there's not much thinking involved.
I like thinking when there's not much physics involved.
Oh, also true. Also true.
Considering you're going to be majoring then, right?
There's no way I'm actually getting into a college, so.
Shoot,
I mean, look at my GPA.
Where are
It's
you
too hard to
going?
get into a good college.
Too high. It's a 4.
All right, correct answer. Tell your neighbor. Correct answer is B. If you flip this over, this becomes a gravity problem. If you just dropped it versus shot it, you have conservation of energy.
So if we drop 2 protons.
Okay, they have the same speed. Good with that? Okay, so we can make the electric potential, just like we can for gravitational potential energy, we can make wherever we want to ground zero. The promise of a potential energy, we can make that ground zero. So we can make this plate have an electric potential of 0, and this plate have electric potential of 100 volts. We can make this have 0. This we have negative 100 volts. You can make this right here in between here 0. So this would be positive 50, negative 50. The important thing is the electric potential difference across the plate is 100 volts. This one's higher than that one as it goes downhill. Sam.
Like with the 12-volt battery,
Yes.
doesn't that just make the whole thing arbitrary? Like how does that work?
We will.
It's changing. It's still 12.
Yeah, it's 12 volts. The electric potential difference between the two is across terminals is 12 is 9 volts.
If we want to be, well, I'm sure I can.
We'll get
Car batteries can have 12
we're
volts, but.
what?
Why did they say the difference was 50?
Yeah. Across those lines, yes.
Oh.
Yeah.
Oh, across these lines.
I don't know.
I don't know.
Across
Literally,
those lines,
they ended the line.
that's a good point.
I pulled this out of somewhere. All right.
He pulled a sneaky one.
Smiley, is this the equivalent of saying like where you set height equal to 0 is arbitrary?
Or what is equal to 0 is arbitrary? H.
Height for gravitation.
Yeah.
Basically. That's the
Yes.
idea.
Yep.
Oh.
Yeah, they're equal potential lines.
Okay. And same.
I studied electricity all weekend.
Tell your neighbor just because I messed up.
Hold up, I don't know. That's just C for. Ooh, wait. No, C for by the outside force.
But then the one.
Oh, by the outside.
Yeah.
Oh, so then.
Yeah.
Tyler has a point. Why is it C?
I didn't realize it was only like that.
3.1
How is your photo thingy? You look so pretty.
But anyway.
Yeah.
Oh. I feel like that's initially.
No.
All right. Correct answer is E. Good job. Okay. This is kind of how I think about it. The electron wants to go this way, so it's like pulling on a dog trying to eat a squirrel. You go to that? Does that make it wants to go? It started at rest, and you're doing negative work. Okay.
I was trying to eat a squirrel and I was eating it.
Okay. Next question. Talk to your neighbor. Tell them why you think so.
So yeah, one of the
People has to be on the right because of the direction.
I was thinking C because it's closer like on the top. I think electric field is closer.
Above the right.
yeah. But what about the voltage?
Because it's going that way, isn't everything?
Because people has to be on the right because the direction of the arrows.
Yeah.
Because it goes from positive to negative.
Well, also because
It goes from
the
high to low.
electric actually passes away from positive.
Fine, yes.
Correct answer is
B.
B. Bountiful buffaloes. Okay. Here it's a strong field. The lines are close together. It's steeper. Okay. Electric fields always point downward to a lower electric potential. Correct.
Okay, I was completely surprised with that because I was like, that's true. The arrows are longer.
I don't know if I can edit this. I can. No, that's fine.
No, actually, it's important.
Oh, because electric fields go from positive to negative, right? So you have your changing voltage is negative on the electron because you go from positive to
There's COVID vaccines and that's typical.
Okay, next question. Okay, this one is jerk question. It's a positive 50 here. It's also a positive 50 there. Most people, when I read this, I was like, that's negative 50 because there's a positive 50 there.
He's twitting. Elon wants to go to Texas for his trial.
Oh, that's right. He said Cali.
No.
I mean, if you want that, you can just kill yourself. You don't have to let the government do it.
All right. Correct answer is B. Beautiful butterflies. Yep. Okay, so they're always pointing towards downhill, which is 0. The lines are close together, so it's a strong electric field.
They don't always point towards 0 because if it's that
Points to it downhill. Point to a lower electric potential. Okay, and then this is weaker. Okay.
I'm doing any of them right.
Tell your neighbor.
I really want to say
But I feel like
0.6.
she's not leaving.
No, look at this. Look at this. How much work am I doing here? Wait, hold on.
What you're doing. I thought.
Technically, right now.
Distance parallel.
How much work does
Yeah,
somebody
yeah,
yeah, grab
yeah.
your circle fork and then do this.
Hold up.
So-
Isn't it?
Right.
Go down.
Oh, that's my data shot of electric.
Okay, what do you want to say today?
After months of reading years, I figured out the people
But I know what you calculated.
Yeah, I know.
Brad, you know what's going on? Man, I love Elon.
But that's distance parallel.
Good old Bolsonaro.
What is yours?
Correct answer is
B.
B.
They're all B.
Yep. So here, the force is going perpendicular to the way you're moving it. To get it to start, you do need to have positive work done, but then you have to slow it back down again. So the negative positive works negate each other. 0.
That one also has an electric field applied. Oh. God, there's so much. 3 bits. Okay. Got it. Multivariate.
I'm just gonna.
I just did arithmetic, so.
Yeah, me too, Isaac. I was kidding.
No, you gotta.
I don't know how you would use calculus out of this.
I mean, I can come up with a way. It's ridiculous.
The area under the graph is the word. Okay.
I wouldn't understand.
I got some cool things then. It was like last week.
If we rotated this around the e-axis, how much?
For-
I was getting everything, but I didn't I guessed anything.
Correct answer is
B.
I guessed it's either B or F.
Not E. I'm afraid of
Wouldn't it be?
Or by the external
Yeah.
force.
the external force. Correct answer is A. It wants to go which way?
Oh, it wants to go that way.
It wants to go uphill. It's a negative charge. Yep, sure can. So, this is just how my brain processes this one. I know, so it's a constant force. It's this constant field. It's force times distance. I just care about from B to C because this is 0. So that's electric field times the charge times the distance. So electric field's electric field's 5 times charge is 0.6. So I've got 3 times distance of 0.5, so 1.5. And then the way I think about it is the force acting on this thing is this way, and I have to move. This is the electric force. My external agent has to move it this way. Doing positive work.
Doesn't that make it do what it doesn't want to do?
It is correct.
But therefore,
That's
it's
why
not
it's
negative.
positive work.
It's the.
The external force is doing positive work. The electrical force is doing negative work. We're increasing potential energy.
Doing this, I'm doing positive work. The pencil, the pen wants to fall, but I'm doing positive work to prevent it from falling.
No, it wants to go. It wants to go this way.
Well, no, I'm doing it
It's
for
a it's a negative. You good? Okay.
Do not know at this time.
Infinitely big.
Let's go.
I got it.
I think it's infinitely big.
Just be safe now.
Infinitely bigger than one. Yeah, can we just say even?
No.
It's me until Smiley teaches. Let's see not an inspiration.
Correct answer is A. Path independent.
The next one's just gonna go off. It goes around the globe. Oh wait. We're playing that thing.
Tell your neighbor.
It has to be. It has to be arithmetic.
Okay, so newtons per coulomb is equal to volts per meter, so it's gonna be 5 volts per meter. And then you're like, okay, so that's half a meter, so 5 volts per meter, but only 2.5 volts per half a meter, so then there's 2.5, and then you know it flows downhill when you do electric field, so boom.
But I think
The D is higher in voltage, like this. A, yeah.
And I was like, oh, yeah.
Sorry.
Correct answer is A. Okay.
It's really embarrassing if the correct answer were B.
So you have electric. Since it's a constant field, you've got this. You could say newtons per coulomb or volts per meter
I love that those are equal.
times 0.5 meters. And electric field always points downhill to a lower electric potential. Therefore, C is lower than B. B is higher than C. Good. All right. So, you remember this last year?
No, I have bad
I don't remember what it means.
Okay. Here's the decipher. Okay, so this is the force. This is the promise of the force, electric field. This is energy. This is the promise of the energy. Okay, to dance between these two, this is from the perspective of the packaging peanut as the test charge. Test charge. This is from the perspective of the thing that's creating the Van der Graaf, like creating the electric field, creating the electric potential difference. Okay. To go between this and this, you have this idea of work. Okay, for force, change in energy. The work done by the conservative force is equal to negative change in potential energy. Force times distance. This is really what we want, is the connection between the promise of electric field and the promise of electric change in electric potential energy. So you get this expression here. Okay, these are vectors, these are scalars. Okay. Okay. Last topic of review:
Oh no.
capacitors. Correct answer is B. Okay. So Kirchhoff's loop rule. This is the chutes and ladders. Like you climb up and you slide down.
Technically, there's going to be some voltage drop over those wires.
Okay. Not when there's no current.
Okay, fine. I'll accept
That's a
that.
good point.
Okay, so you have a voltage gain. Any loop that you draw, even throughout space, the voltage gain equals the voltage drop. A little crazy. Okay. Right. So when we're talking about capacitors, these are like storage tanks for electric energy. This is the future of batteries. Like just there's a lot of research going into how do we store electric energy in capacitors. Okay, so the analogy is it's like a pressure tank. So it has an expandable bladder, so you can pump water into here, and that fills up. But there's pressure pushing back that wants to push it out. Okay.
Did you come up with anything good for actually storing electricity for these?
Yeah.
Yeah.
Oh yeah. Yeah,
Well,
like
on a computer sometime. I recommend that you have an anti-static bracelet around your ankle, and actually in that bracelet being grounded. But yeah, open up a computer sometime. You'll find a bunch of capacitors.
I mean they've got in electric cars. I'm pretty sure they've got a combination of capacitors and batteries. Like there's a lot of research going into this because it doesn't take chemicals, and they're more their life expectancy is higher than a rechargeable battery. So there's a lot of pros. So the pressure is analogous to the voltage. Capacitance is analogous to the diameter of the bucket or how big the bucket is. And charge is how much water is being stored in that pressure tank at a given point in time. Okay, so this is the schematic diagram symbol. You got two parallel plates is the simplest. There you go. Arrangement for capacitors. They always have equal charge, the area and the gap distance between the two. Okay. So nice thing with capacitor is the electric field is constant. We have this is a familiar sort of VED. Voltage is equal to electric field times the distance. Okay. This is permittivity of free space. This is 8.85 times 10 to the negative 12th. Okay. This is the charge on one plate over the area of one plate is equal to the electric field, the strength of the electric field. I'm pretty sure these are both on the, let me check before I say that. I think that's on the equation sheet. You guys, equations. Nope, just kidding. That's a sad day. All right. Not on the equation sheet. Yeah.
We don't have. Well,
Well,
voltage is field times distance. That's just a definitional thing, assuming constant field. So we can. So we don't need to. So you don't. So that might. So without capacitor, that might be on.
we'll come up with a way to make that a little bit easier to remember later on.
Smiley, it's area, not volume, right? So it's
Correct.
2D.
Area. Yep. Yep. Okay.
No, but it doesn't.
Okay.
No.
It's supposed to be.
Okay. So capacitance is the ratio of how much charge can be held in a capacitor for a given amount of voltage. Yeah, that's what capacitance is. It's coulombs per volt.
Say that again.
It's how much charge could be held in a capacitor for a certain amount of voltage. Okay, so for the pressure tank analogy, if you have a pressure of like 20 psi, how much water is going to be held in that tank? Okay. Obviously, if you put more pressure, you're going to have more water held, but for a given amount of pressure, how much water is stored in that tank? So it has to do with how big the tank is, this idea of capacitance. Okay. Now, this is, I think I ran through you or with you through last year, but last year, so resistance is equal to voltage over current from Ohm's law. Okay, and we can figure this out. We can find the resistance experimentally, but in reality, the resistance of a wire is given by the resistivity times the length over the cross-sectional area. This is actually the geometry, the physical stuff that causes resistance. We have a similar expression, similar relationship with capacitance. This is experimentally, we can figure this out. But in reality, what defines that is the geometry of the capacitor, where we have the area of the plates over the gap distance multiplied by this permittivity constant. Okay.
Well, we could just increase the value of that permittivity constant to increase capacitance.
True, we could. Okay. So I should list all these equations because my brain doesn't fit all of them in there. I don't know why I haven't done this until then. Go ahead and figure that out. This isn't too bad. It's all right.
Smiley, do you want to fix this?
Do I want to what?
Oh, never mind. I thought you were going to change the screen. I agree.
Okay, tell your neighbor the answer to this question.
C is the same. When E goes up, Q goes up. B goes up.
10 goes
So
back to
Q
one.
is bigger on C.
Yeah.
On C. Pure bounce.
You got kidnapped. Don't say it's kind of scary.
He is evil to death. Finally. Physics.
Wait,
What did you say? It's scary.
Okay, correct answer is
B.
good. B.
Easy go to there. So see you don't be at like
Daniel. When you do this,
I just
giant real.
Good answer. But they're trolling. They're so trolling.
This person tries.
See, this is why I just like this is why I just use lot that.
Colin's getting trolled.
Goblin?
Yeah, watch it.
We
No,
play
it's
irrefutable
There was this guy. He
looks like one of those little dumb
frogs.
Okay, next question.
I think actually people are convinced of this. Yes. People are and now they're arguing over which mythical monsters are real in the government.
I wish that Yetis were.
They are. The government's hiding.
Yeah, the government's not hiding.
What if the Yeti does? I love that.
The government's not caring.
Next question.
No.
Why are they what? The same thing. I'm just typing these equations. Oh, I got that right. Stink.
Nice. Can I yell to you? I hope to your brain's confident, but I Oh no, what's happening?
Nothing. Okay.
Charlie, it's either B, it's either C or D.
I think it's
I think it.
because capacitance is going to
down.
decrease. So
So Q
taking
has to go
voltage
down.
the same. Yeah, Q has to go down. Yeah.
Well,
How we
technically,
why are they using about we're gonna set another voltage for
Too bad it was not made. Doesn't.
Oh, there it is. Go, Isaac, go. Catch it. Oh, you caught it.
I'll get to you at the end of class.
No. Wow. I'm getting another up by second.
What the heck? I didn't like this compared to my Spanish teacher, so I gave it back to you if you can compare it.
I don't know.
That's hilarious. Correct answer is
Smiley, don't you just love teaching?
I do. Okay, so here's the thing I want you to take away. As long as your capacitor is hooked up to your battery voltage source, the voltage across these plates are going to be the same. So you keep this the same. So we're increasing the distance, decreasing the capacitance, the area stays the same, voltage stays the same, capacitance goes down, so charge goes down. C.
What equals what is
Okay.
that equation? What is that fourth equation for?
I'm in the midst of fixing it. All right, so you're using, you can either go this approach, or you can go this approach. No. Electric field.
Oh, you go through E.
Oh, this?
That does not look like a
That's a permittivity of free space. 8.85 times 10 to the negative 12. Okay. This question
I know the answer.
is just to show you how big 1 farad is. Okay. So this is This is why.
So let's go back.
This is why we do microfarads or picofarads.
Yeah, that should be our new thing.
Are coulombs only the way they are so that newtons per coulomb is equivalent to volts per meter?
No.
Why are they so?
Hey,
Well, no, we
Knee jerk reaction. I'm just making this up. Is I think it's a consequence of the fact that 1 coulomb is a huge amount of charge. Where that came from is we defined coulombs based on originally from circuits, and there's a lot of electrons going by certain, so like so I that's it, we're
Yeah, it was awesome. What was the name? You had to be there. I was there.
Really funny.
I know, I'm so.
Yeah. All right. Next question.
If I would have cut it, I would have been so sick. You have to with the whole
Okay. So the takeaway I want from this is if you remove this, then the charge is isolated. It can't go anywhere. Okay.
Wait.
The charge remains constant.
So doesn't the voltage remain constant?
Nope.
No, because the capacitance decreases.
So
Well, at least you're having a Monday.
That's actually
all right. So your capacitance decreases, charge remains the same. So if this decreases, voltage increases. You can look at it that way. You could also look at it this way. The area is not changing. The gap distance is increasing, so the electric field goes down. Electric field goes down. Gap distance. Yes, Sam.
In terms of voltage being the elevation, how does that work?
Because you're increasing the. Hold on. Why is this not working? Your gap. Is this right?
Is what right?
That equation right?
I was right the whole time.
No, wait.
I was wrong. That's what was messing me up. So sorry. Electric field. That's not A. That's not D. That's sorry. I know. I messed this all up.
Wait,
That-
what the original equation was?
I'm looking at this. When I
Hold up, I am.
my bad. I'm teaching you guys wrong.
Like the
That's
whole
right.
time.
No. Just
This is the original one I would done. Was this also?
this one's correct.
I have capacitance capacitance as permittivity times area over distance. Is that wrong?
Oh, I see.
Oh, electric field is.
Yeah, electric field is what it's screwed up on.
Got it.
But that question wasn't involving the electric field.
Yeah, it could be. Here we go. Ready?
Buckle up.
All right. So the charge is not changing. The area is not changing. Therefore, the electric field is not changing.
Because we said that a particular constant is not changing.
Correct. It's constant. The electric field stays constant. The distance increases, and therefore the voltage increases. Sam, to answer your question, how does this correspond to voltage and elevation? You are so between the two plates, it would take a certain amount of work to take this to move it to here. That distance got bigger. It would take more work to take it to move it to here. Like actually I should go the other way because we're taking electrons. It would take, we're taking an electron off of here. No, I did it right. Take an electron off of here and pushing it over there. It doesn't want to do that. So it'd take more work for it to move it from here to here, bigger distance. Just like it would be a higher elevation for gravity. You all right with that?
Oh yeah, because electric field is the same.
Mm-hmm. Okay, for the sake of time, I want to quick hit these things. So if you have parallel capacitors, you are essentially, you're doubling the area, which increases the capacitance. Okay, if you have capacitance in series, that's essentially like combining the gap distance, which decreases the capacitance.
You're adding their area, right, and adding the distances.
Yep.
It's a bit more complicated.
Okay, so here is the relationship for series and parallel. With resistors, bring it back to circuits and Ohm's law, which I think you're more familiar with. Okay, in series, the current's the same for resistors in a circuit. Okay, for capacitors, the charge is the same. Okay, the voltage adds up in series. Okay, and that happens with resistors and capacitors. Okay, in parallel, the voltage is the same, and the current adds up, and for resistors, and the charge adds up for capacitors. Okay, and so using that, we find this expression, and for parallel capacitors, you add capacitance up to find the total equivalent capacitance, but in series, you end up doing the 1 over C, just like for total resistance in parallel. Good with that? Remember that? Kind of bringing that back. So those are factoids there. And then lastly, let's see, don't want to do that to you. I'll do this to you. Lastly, you got these problems. These were like towards the end of the chapter with capacitors. So you charge this up, you charge this capacitor up, and then you disconnect the battery, but then you take this fully charged one and you charge the other one. Okay. If these have the same capacitance, well, here's really the takeaway. Here's what this is the facts that you really need to own. What conditions are true? Tell your neighbor. Okay, let me just throw out this. Here's what's always true: Kirchhoff's loop rule, Kirchhoff's junction rule. Okay, in this case, you're just going to do Kirchhoff's loop rule: voltage gain equals voltage drop. Thinking about series and parallel falls apart because this series and parallel, those circuits assume that this voltage source remains constant. When you're charging something, or like when you're using a capacitor to charge another, this voltage doesn't stay 10 volts. As charge leaves this voltage decreases. So you can't say, oh, it's series or it's parallel. Like, ooh, don't do that. It doesn't work anymore.
Why not? Because you can't get.
Oh, they have different capacitors.
Yeah.
Okay.
Okay.
Yeah, it's only 2 arbitrary.
Here we go. Here's what you got. You got charge initially is equal to capacitance times voltage. So you get a total charge initially of 20 microcoulombs on C1. When you switch this over, your total has to equal 20 microcoulombs. Okay, the conservation of charge has got to be somewhere. Okay, this is going to happen until they have the same pressure. Okay, as charge leaves off of here and goes into here, the voltage across that decreases. Does that make sense? As charge comes off this capacitor and goes into that, the voltage across this no longer is 10 volts. It's something less. It's going to go until these voltages are the same, because voltage gain has to equal voltage drop. Okay? It's not 10. It's probably not 5. It's somewhere. I mean, it would be 5 if this is identical. Okay? Woo! Yep.
How does that work? Like, what
If it-
tells us that the voltage is gonna drop off?
It has to drop off because you're losing charge.
Oh, okay, yeah, and it's capacitance.
Correct. Capacitance stays the same.
Mr. Smiley. Oh shit, I'm in the video.